Assalamu alaikum. Good morning, everyone. My name is Dr. Nafisa Noor. I'm an assistant professor at the Department of Electrical and Computer Engineering at the North-South University of Bangladesh. First of all, I would like to thank the conference organizers for inviting me to the talk. I'm also thankful to the respected chairs and the host for the introduction at the beginning of this session. Welcome to my presentation. In this talk, I'm going to talk about the stochastic properties of phase change memory nano devices in the hardware security application. So I'd like to start my presentation with a brief introduction on the hardware security field because I assume that my audience would be the most interested to learn about this new field. In very general terms, safety, security, and privacy are prime needs of human civilization. From the ancient era, people have been trying to protect their personal belongings using various forms of mechanical lock and key systems. Despite the enormous improvements of these mechanical lock and key systems, they still fall short in the current age of Internet of Things or IoT. The need for the hardware security is very much interlinked with the IoT. Because in the IoT era, we do a lot of the personal and business related activities or transactions over the internet using the data exchange structure, using various forms of controlling devices. These controlling devices are small, portable, and hence are easy to lose. So it's not uncommon if these devices are under the control of some malicious attackers. So in the current age of IoT, we not only have to protect the cyberspace from the hackers, but also we have to make sure that our controlling IoT devices are under good protection. So we need to protect these IoT devices, and that is what we mean by hardware security. Say, for example, if you consider the smart home system, in a smart home system, we need to control some sensitive parameters of home, say for example the room temperature or humidity. Also in a smart city system, several sensitive and essential sectors, for example the agriculture, transportation, traffic, healthcare, education, and many other essential sectors are usually controlled by assigned authorized personnel, and we certainly do not allow any malicious intervention or unauthorized access to those devices. As a solution to this problem, we can install chips to these hardware devices for providing security. The traditional way is to store a permanent key in a memory of the RFID tag. But the problem of the permanent key storage is that if the tag is stolen by an attacker, the attacker can directly measure all the permanent keys using the advanced reverse engineering tools and microprobing attacks, and thereby the attacker can produce counterfeit or clone chips. Now, these counterfeit or clone chips not only causes problems or losses to the legitimate companies that produce the original chips, but also it poses serious threats to personal lives and national security. So say for example, if that tag is used for accessing a restricted area, then with those counterfeited chips or tags, anybody can access to those restricted area. So that's not what we want. So for hardware security, we need to rely on processes that are inherently unclonable. So if the attacker has full possession of the device and tries to look into the device through advanced reverse engineering tools and attempts to fabricate a similar chip, the attacker should always fail to produce a clone. And these devices themselves should be generated with such random features that even the manufacturer cannot produce a clone. The physical unclonable functions or puffs can meet that security requirement. Now, what is a puff? A puff is a hardware which is interrogated with a certain input called the challenge C, and it generates a unique output which is called the response R. And this response is produced based on the complex functionality that are inherent to the device or materials used for building the PUF hardware itself. Now, there can be various challenge response pairs in a PUF, and these pairs are called CRPs or challenge response pairs. Now, say for example, for a challenge C1, the response can be R1. For a challenge C2, the response can be R2, and so on. Now, there are a few important metrics related to the PUF. Say for example, for a certain challenge C1, the response should always be R1 reproducibly, and that is called the reproducibility feature of the PUF. Another important feature or metric for the PUF is the uniqueness. And according to the uniqueness, when a certain challenge C1 is applied to two different PUF chips, they must produce two distinct responses. For example, R1 and R2 in this case, where R1 and R2 must be distinguishable from each other. So you can compare these two properties with the fingerprints that we have with the human hands. Say for example, when we try to look at the fingerprint of a specific person, we want that the fingerprint of that person would be the same every time, and that must be similar to the reproducible property of the PUF. Also, when we look at the fingerprint of two different people, we always want that for the two different people, the fingerprints must be distinguishable, and that property is similar to the uniqueness property. Now, because of this uniqueness property, whenever the attacker tries to produce, or even the manufacturer tries to produce a similar chip, that chip would always give a very distinct response whenever it is interrogated with the same challenge C1. And that is why the PUF is unclonable, and that is the reason why even the attacker or even the manufacturer cannot reproduce the PUF itself, and that is the unclonability feature of the PUF. Now the question is, how can we generate a chip in that way? So the answer would be there are various ways that we can exploit. Say for example, if we consider the photolithography process, then we can produce the devices in the nanoscale and they would all look different. For example, the transistors are all different when we produce them using the photolithography process. Also, we can think about the synthesis of the nanomaterials, and every time we produce using the exactly same procedure, they would still vary in their dimensions and orientations. So in this talk, we're going to use not only the photolithography processes, but also the physical variations that we have in the phase change memory nanodevices. The conventional PUFs are CMOS based and rely solely on the process variations. However, there are some problems of these conventional PUFs. For example, there are some PUFs where the adversary can make exhaustive measurements. So when these exhaustive measurements are done, all the challenge response pairs can be measured and the security of the PUF is broken. And there are some other types of PUFs where there is linearity inside the circuitry. Hence, when the adversary can measure only a few of the challenge response pairs, the others can be predicted because of the linearity of the circuit using the machine learning attacks. Hence, the security of these PUFs are also not ensured. Hence, recently PUFs are being proposed using the emerging non-volatile memory technologies, where several physical variations are present in addition to the typical process variations. Here you can see the memory cell structures of the three most researched emerging non-volatile memory technologies. And phase change memory or PCM is one of them. Interestingly, all of these three technologies offer a very important physical variation, which is known as the programming variability. Programming variability means the inability to program to a certain memory state. An important point to note here is that this variability exists not only in different cells of an array, but also in different cycles of the same cell operation. Before we go into the depth of the programming variability, I'd like to briefly introduce PCM here. PCM is a fast, dense, non-volatile memory technology. There are various cell designs reported for this memory device. The one that you see here is known as the mushroom cell. In most of the designs, the common feature is that there should be a phase change material between two electrodes. The most commonly used phase change material is germanium antimony telluride. PCM has two memory states. The high resistance state is known as the amorphous state or HRS, and the low resistance state is known as the crystalline state or LRS. To switch from the low to high resistance state, a brief reset pulse is applied so that the temperature inside the phase change material exceeds the melting temperature, and then the material is quenched sharply during the short fall time of the electrical reset pulse. The sharp quenching in the reset pulse results in the disordered atomic structure of the high resistance state or the amorphous state. This process is also known as the amorphization process. To switch from the high to low resistance state, we apply a set pulse. The set pulse has a lower amplitude because this time we do not have to melt the material, and the set pulse also has a long fall time at the end, during which the atoms get enough time to go to their ordered crystalline structure. So this process is also known as the crystallization process. To read the cell resistance at any state at a certain time, we need to apply a non-destructive low voltage read pulse or a DC sweep. Now, the programming variability may result in a slightly different program resistance level than the targeted one. The programming pulse parameters can also be further tuned in such a way that it can result in either a successful reset or an unsuccessful one. Now, similar uncertainty can also be achieved with the set operation, but we prefer the reset operation to the set operation because the reset process involves melting and can be very distinct on different reset operations, no matter whether we are applying on different cells of an array or different cycles of the same cell. So from cell to cell and also from cycle to cycle, we can have the strong programming variability using the reset uncertainty. Using the reset uncertainty of PCM, we can develop a binary path. The idea of a binary path is very similar to the uncertainty involved in the coin flipping, where each of the two possibilities have a 50% chance and there exists no intermediate options. To utilize the reset uncertainty for path, we need to start with the crystalline state, then apply a single reset pulse with a moderate reset voltage amplitude, and then check whether this cell is reset or not. We observe that certain cell dimensions and cell designs can enhance the programming variability even further. For our experiments, we used the GST 225 line cells that are fabricated at the IBM T.J. Watson Research Center. These cells are 50 nanometer thick. These are on silicon dioxide. They have bottom metal contact pads and are capped by silicon nitride. We anneal these cells up to 650 Kelvin temperature inside a cryogenic probe station to reach to the stable hexagonal close-packed or HCP crystalline state, and then perform the electrical characterizations at a room temperature probe station. We used 9 different dimensions of these cells to check which ones are good for puffs. For each cell dimension, we used at least 20 cells and we applied a single reset voltage pulse to each cell. But before testing the puff performance, here we are doing the pre-calibrations. Different cells in each group experienced different pulse amplitudes. The low amplitudes always resulted an unsuccessful reset, while the high amplitudes would always reset successfully. And what we needed to check is how the moderate amplitude pulses program. What we found here is that the wider and shorter cells program quite linearly, which indicates a controlled programming, which is not what we want for the puffs. Slight variation is present here as well due to the cell-to-cell process variations and the programming variability itself, but that slight variation is not enough for a binary puff. In contrast, what we found for the long narrow cell is that the moderate pulse amplitude gives a very good uncertainty where we get some cells that are reset successfully while some others not. And that is exactly what we needed for a binary puff. The moderate pulse amplitude for which we get stronger programming variability are highlighted with the green areas for the long narrow cells. We defined our own HRS, which is the successfully reset cells, and the LRS as the unsuccessfully reset cells. The large separation between our HRS and LRS excludes the need for additional circuitry to calculate the threshold to distinguish the two states in a binary puff. Instead, in our design, the threshold already exists between the HRS and LRS, and the threshold is more than 2 orders of magnitude large. The white cells are difficult to reset fully, and that is the possible reason for having many intermediate states, whereas the narrow cells block the conduction path and have a higher tendency to either reset fully or to fail. So we certainly prefer the long narrow cells for puffs. Another important way to improve the programming variability is to apply voltage pulses instead of the current pulses. The initial crystalline state before the reset pulses were applied is also a programming process and includes variability. In our case, we annealed all cells inside a cryogenic probe station. And in many practical cases, this initialization is done using the electrical set pulses. In either method, the set variability would result in a stochastic crystalline resistance distribution. This stochasticity is present in cells of any dimension. And here you can see the distributions found in the long narrow cells, and here you see the distributions found in the wide long cells. Hence, it is evident that this crystalline initial resistance distribution or statistics is found in cells of any dimension, and it is worth utilizing this previous crystalline initial resistance distribution to enhance the overall programming variability in the later reset stage. Hence, it is more meaningful to apply voltage pulses to utilize this variability. By using the same applied voltage pulse amplitude, the applied current amplitude would be different on different cells due to the stochastic crystalline resistance present in the initial resistance distribution. As a result, some cells will experience melting and quenching, and thus they will amorphize, whereas the others will not experience the amorphization. Hence, we can have a more successful binary PCM puff. Apart from the variations, we also had some parasitic components in the experimental circuitry. From our detailed SPICE circuit simulations and finite element device modeling results, we observed significant variations in the melting locations and the crystalline grain distribution map after each reset pulse on the same cell was applied. These parasitic components can be easily integrated along with the PCM cells to enhance the reset variability. Now that we have investigated so many different contributing parameters for the programming variability, we are ready for performing the puff test. For the test, we have used 85 long narrow cells. These cells were 130 nanometer wide and 456 nanometer in the length. And we already described that these are 50 nanometer thick cells. We took these 85 cells and we applied the exact same uniform programming approach where a reset pulse of moderate amplitude of 1.5 volt is used. Apart from the moderate pulse amplitude, we also noticed that by using the short transition rise time or fall time, we can also enhance the programming variability, because when we have faster transition at the rise and fall times, the capacitive components can contribute to significant currents from the parasitic components of the experimental circuitry, and that adds to the programming variability even further. Now, after performing the test whether the cells are resetting or not, we noticed that among these 85 cells, 50% of them are reset, which we define as the high resistance state, and the 50% do not reset, which we define as the low resistance state. And we find this significant distance between the high and low resistance states, which is almost 1.5 orders of magnitude different. And because of this difference, we really do not need any reference cell array, which is another similar looking array as the main array. And the threshold is usually calculated from this reference array. But in our case, we do not need this reference cell array because our threshold is pretty wide, and this is clearly evident between the defined HRS and LRS of this design. We measured these 85 long narrow cells after 9 months, and we noticed that the high resistance state cells are shifted to even higher resistances because of the resistance drift of the amorphous state. And we also noticed that the low resistance state cells are shifted to even lower resistance values because of the crystallizations of these intermediate or mixed cell states. So after 9 months, our separation between the high and low resistance states is almost 3 orders of magnitude, which is almost double of the separation that we had right after the programming of these cells. So this is great that we observed no bit flipping at all for these 85 long narrow cells, and that also ensures the reliability over aging for our binary puff design. Now I would like to summarize this work. We have used phase change memory based puffs for hardware security applications, and for this purpose we have used the programming variability of the reset operation of phase change memory. There are multiple ways that we have utilized to enhance the programming variability, and these methods are to use the long narrow line cells, to use the voltage pulses for programming instead of the current pulses, so that we can also utilize the crystalline resistance variability before resetting these cells. We have used pulse engineering so that the parasitic components from the experimental circuitry is also utilized. Finally, this work was supported by the United States Air Force Office of Scientific Research, and the experimental characterizations were done at the University of Connecticut, and the devices were fabricated at the IBM T.J. Watson Research Center. Finally, I would like to thank my audience for your kind attention. Thank you very much, and I'd like to take any question from you.